Good morning, everyone. My name is Virendra Singh. I am Senior Materials Engineer with Schlumberger. First of all, I would like to thank organizer to arrange this symposium online during this pandemic time. I pray for everyone health and safety. Now let's move to the presentation. So here onwards, I am going to stop my video and focus on presentation and do not want to use my internet bandwidth. So, all right. So my topic of presentation is electrochemical corrosion behavior of nitrogen-enriched stainless steel. Let's move to the next slide. Okay, for oil and gas services, several alloys are used to manufacture downhole tools, starting from low alloy steel to corrosion-resistant alloys, such as different grades of stainless steel and nickel alloys. These downhole testing tools are used to determine reservoir pressure, temperature, permeability, and productivity. These downhole tool testing tools are used in different hostile conditions, such as in different high differential pressure, temperature, and different H2S and CO2 environment, and also used in different geographical location at the same time. And these tools need to meet industry regulation such as NACE and API standards. In such environment, we need high strength corrosion resistant alloy for short to long services depending upon the operating conditions. In order to operate effectively at low cost, stainless steel are preferred in CO2 and mild H2S environment. For example, 13 chrome and super 13 chrome and 17.4 pH stainless steel are these are high in yield strength and high fitting potential than lower alloy steels. However, they are not good in galling and wear and scratch resistance due to low in hardness, and they got damaged during assembly during operation. Therefore, these alloys are often plated with electroless nickel and copper, which eventually flakes off during operation due to poor adhesion. Okay, surface treatment such as nitriding and nitrocarburizing process are some options for surface hardening of for these stainless steel to improve wear and galling resistance. These are the thermochemical process where nitrogen and in nitriding process and nitrogen and carbon nitrocarburizing process uh, diffused in the lattice of the metals. This operation produces nitriding and carbide uh, on surface. In case of chromium rich material, they form chrome carbide and iron nitride. So this diffusion treatment generally carried out at 900 degree Fahrenheit to 1100 degree Fahrenheit, and time of operation can vary from 2 hours to 20 hours. So let's discuss briefly on experimental section. In this study, we selected 5 different stainless steel material. These alloys are extensively used in downhole service and permanent tool. 13 chrome and super 13 chrome uh, and 17.4 pH stainless steel are martinistic stainless steel, whereas 13 chrome and super 13 chrome are quench and tempered stainless steel, and 17.4 pH is precipitation hardenable steel. 17.4 pH is having more than 15% chromium, the same time nickel and copper, whereas 13 and super 13 chrome is having 13, close to 13% chromium, whereas super 13 chrome is having 2% molybdenum. We also use two austenitic stainless steel grade, 316 and 304. 316 is having chromium close to 17 at the same, but the nickel is higher in this case, and there is a 2.5% moly in 316 grade, whereas 304 is free from moly. Okay, this slide shows the mechanical properties of these alloys. We can see from this mechanical property data that they are high in yield strength and tensile strength, that is good for oil and gas application. However, hardness is not sufficient to prevent them from wear and galling and scratching. Here we can see the hardness for 13 chrome is max 22 HRC we use. Same with super 13 chrome, we're max 28 HRC. And 360 and 304, any stainless steels are softer. So in this study, we subjected these material to same kind of treatment, that is nitrocarburizing diffusion treatment to improve surface properties. So different coupons of these materials were subjected to salt bath carbonitrizing process at 1100 degree Fahrenheit for 2 to 3 hours. So we have used industrial setup to mimic the same condition as done on the parts. So this is kind of different from lab environment. So we have used proprietary salt chemistry to diffuse nitrogen and carbon and form surface nitrides on these material. Further, to evaluate corrosion properties after nitriding, they were subjected to cyclic potentiodynamic polarization test as per the ASTM G61. So testing is done at room temperature, 23 degrees centigrade, and 3.58% NaCl solution. We have used Gamma 3 electrodes flux cell. So the importance of this flux cell is working area or working electrode area is 5 centimeters square, and we do not see any crevice corrosion effect. So in all the testing, we do not have any crevice corrosion, and we have the clear data on all our test samples. Okay, now let's discuss about the results of the study. So after nitriding, samples were evaluated for nitriding depth. As we can see from this microstructure, formation of continuous layer of chrome nitride with traces of iron and nitride formation, which is well established in literature that on these stainless steel during nitriding operation, we form predominantly chromium nitride and traces of iron nitride. That is established by X-ray diffraction study. So thickness of nitride layer depends upon the time and temperature and alloy composition. In this particular study, time and temperature we kept constant, therefore alloy composition control thickness of the nitride layer. Alloy rich in chemistry such as 316 and 17.4 pH have thinner nitride layer compared to other material. That could be due to high nickel and moly content, so which does not allow to form or diffuse nitrogen and carbon in the lattice, whereas 13 chrome shows relatively thicker nitride layer. Okay, further microhardness testing was carried out on cross section, which is important to make sure nitride layer is hard enough for wear resistant application of these alloys. All the material shows hardness in the range of 1050 to 1100 noob hardness. It is important to note that the hardness of the material after nitriding operation fall below the nitriding layer. Here we can see the size of the indent increases as we go deep, and also from this plot we can see surface is hard and immediately it drops to the base metal hardness. Now let's discuss about polarization study results of untreated alloy first. So results are plotted together for comparison. This plot is on current density and potential. As we can see from these plots that untreated alloys like 13 chrome and super 13 chrome shows lower open circuit potential, and the current density sharply increasing due to rupture of inherent passive layer, generally the chromium oxide layer on surface, so which is indicated by serration in the plots of 13 chrome and super 13 chrome material, whereas 17.4 pH, 304 and 316 still shows typical passive uh, passive behavior and pitting and repassivation behavior. From the plot, we can rank the material based on the pitting potential, like 316 is having higher pitting potential than 304 and 17.4 pH. And then also repassivation potential is higher for 316 and 304, where the lower current density for chromium rich alloys was seen compared to 13 chrome and super 13 chrome material. After nitriding in these alloys, uh, stainless steel samples, we see interesting corrosion behavior. Nitriding treatment raise OCP and corrosion potential and have slightly influenced corrosion current. Interestingly, no pitting behavior observed uh, as we have seen in the untreated material. This is due to the thick chromium nitride compound layer formation on the surface of each alloys. So this compound layer acts as a passive layer and does not allow increase in current density, as we can see. As we can see from these plots, we also observe a repassivation behavior in backward scan after nitriding these alloys. This indicates that the thick nitride layer is protective and current potential is unable to break this passive nitride layer. So this slide shows the electrochemical parameters which is extracted from the polarization plot as I have shown earlier, and these data is summarized in this table. We can observe from this plot that OCP and corrosion potential has improved for each alloys after nitriding treatment, and they are more towards like increased side, and where we can see 13 chromes, super 13 chrome and 17.4 pH, and for all other two alloys it has increased. Further microstructural examination was carried out for untreated and treated samples after corrosion test. So we can see untreated surface has many corrosion pits after polarization test, and whereas the treated surface was not susceptible to any kind of pitting. So this we have seen for 13 chrome and super 13 chrome material. So these samples look like kind of black and dark color. That is because of the uh, nitrocarburizing process, but no pits were observed. Similar behavior observed for 17.4 pH and 304 stainless steel and 316. So untreated surface of 316 stainless steel shows some microscopic pits at high magnification. whereas no pitting observed after nitriding. So at the end of the talk, I would like to conclude my study that nitriding treatment significantly increases surface hardness of stainless steel alloy through nitride formation. Compared to untreated alloys, nitrided stainless steel exhibit higher open circuit potential and corrosion potential and low corrosion current. Nitriding surface treatment creates a hard compound layer, which is passive in nature, and pitting corrosion resistance increased after nitriding treatment in current test condition. Okay. Let's go to the next slide. All right. Thank you for listening my talk. So I will discontinue here.